Hello and welcome back. Today we are going to be looking at optical activity. So enantiomers exhibit identical physical properties, and that should make sense because physical properties are determined by these intermolecular interactions between the molecules, but some enantiomers do exhibit different behavior when they're exposed to plain polarized light. So let's quickly review what the nature of light is. So, as we all know, light is called electromagnetic radiation because it has an electric field and a magnetic field. And those are oscillating together. And there's some polarization of the wave, which is the orientation of the electric field, because normally they're perpendicular to each other. But if we polarize it, we will only have the electric or the magnetic wave going through. So typically it's only the electric wave. And that's called plain polarized light. Now, what happens if we polarize it in one direction, let's say vertically, and then we polarize it horizontally? What's getting through? The answer is nothing, because all of it is blocked. Because we're filtering out one of them, which is either the magnetic or the electric, and then we're filtering out the electric or magnetic that wasn't filtered out earlier. So that's how light works, or electromagnetic radiation, whatever you prefer to call it. And that's more on the physics side. Now let's get to the chemistry side. So what do we call this stuff in chemistry? We call this polarimetry. And polarimetry was developed by this guy named Jean-Baptiste Biot. And he was exploring the nature of light by passing plain polarized light through many organic compounds, including methane, blah, 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 blah. And he discovered that solutions of certain compounds rotate the plane of the polarized light. And that is actually pretty interesting. Those are said to be called optically active, and the ones that do not have that cool ability are called optically inactive. And now he developed this neat thing called a polarimeter, which looks kind of like the illustration on the screen. And you can see a light source comes in, it gets polarized, and then we have a rotatable polarizer on the other end. So we can look at it and see what happens, and see either an observer or a molecule at the other end. See what happens. Alright, so now we're going to look at specific rotation. So when we have a solution of a chiral compound that's placed in a polarimeter, the observed rotation is dependent on the number of molecules that the light encounters as it travels through the solution. Which obviously depends on the concentration of the solution, right? But what is the specific rotation? So we know with the observed rotation, but the specific rotation is the observed rotation under some standard conditions, which is 1 gram per milliliter, and then there's a standard path length, which I believe is 1 decameter. And yeah, so we actually have an equation that we use for the specific rotation. Let me write that on the board. Alright, so there it is, and there are a lot of variables in here. So we have the d variable, which is the distance. Wait, no, sorry, that's the alpha, actually. And the alpha is specific to the compound. Next, we have c, which you may all know from physics is the speed of light. And then we have L, which is the wavelength of the light. And that's how we calculate specific rotation. So now, what do we call these compounds when they have different rotations? Well, positive rotation is called dextrorotatory, and then negative rotation is called levorotatory. So that's what we call them. Alright, we have one last thing to look at before we close out this section, and this is called an enantiomeric excess. So a solution containing a single enantiomer is optically or enantiomerically pure. Therefore, there's only one enantiomer, so the other one's completely absent. But when it contains equal amounts of both, it is called a racemic mixture, and it will be optically inactive. And there's a way of calculating that. So that percent of the enantiomeric purity is basically the alpha of the mixture divided by the alpha of the pure enantiomer. And we multiply that by 100% to get it as a percent. And that's it.